This is attempt 2 at 10.6. My mic wasn't working for the first one. So I already wrote out most of this. I'll just kind of read through it here. 10.6, we're looking at alternating series. So just a quick definition of an alternating series. An alternating series are where the terms are going to alternate positive and negative. So positive, negative, forever and ever and ever. Quick little theorem here. So this is the most important thing coming from this section called the alternating series test. So just a quick little definition. So here we're going to define an alternating series. It's very important that you have this negative 1 to the n plus 1 term out in front. This is what's going to make it alternate positive, negative, negative. And then we have our sequence terms here, these u sub n. These are always going to be positive, and you'll see that down here in just a second. So just writing it out, you have a positive u1, the first sequence term, minus u2, the second sequence term, plus u3 forever and ever to complete your alternating series. Now this alternating series is going to converge if the following three things are true. If our u sub n's are always positive, so if you write it out the correct way with the negative 1 to the n plus 1 out in front, our u sub n's, this will always be true. The second one is the hardest thing to prove. I'll show you how to do it very easily though. So the second thing, the u sub n's are eventually non-increasing. So here, eventually, u sub n is going to be greater than or equal to u sub n plus 1. It's going to be a decreasing sequence to make our series eventually go down to 0. Notice that it says eventually. It doesn't always have to be non-increasing. It's just that there has to be some index value that it's always non-increasing after that. The third thing that has to be true is that your sequence, u sub n, has to go to 0. If all three of these things are true, then your alternating series converges. Here's a quick little example, the alternating harmonic series. So my alternating harmonic series, the sum as n goes from 1 to infinity of that negative 1 to the n plus 1, and the harmonic part 1 over n. I wrote out some terms here, so if I plug if I plug 1 in for my n's, I'm going to get 1. If I plug 2 in, I'll get negative 1/2, positive 1/3, negative 1/4, and so on and so forth. It's the harmonic series, except it alternates positive, negative, negative. If we look at the three different conditions, our u sub n is going to be the 1 over n part. That is always positive as n goes from 1 to infinity. My u sub n's are eventually non-increasing. As I keep plugging my index values in, it's going to make my denominator bigger, which is going to make my 1 over n decrease forever and ever. The third thing is that my the 1 over n u sub n part does go to 0. So if I plug infinity in for my n value here, this goes to 0. So that third part is true as well. And because all three of my conditions are satisfied, the alternating harmonic series does converge. I have one little bit more complicated of an example down here. So consider the sequence where u sub n is this, 10n divided by n squared plus 16. So of course, we're going to be looking at the series, negative 1 to the n plus 1 of these u sub n values. The question is going to be, does this converge? To see if this converges, this is an alternating series, so we're going to use the alternating series test. The first part of the alternating series test is that my u sub n's are all positive. Well, u sub n is this 10n over n squared plus 16, and as long as I'm plugging in positive index values, which is what I'm going to be doing, these will always be positive. The second thing is that my u sub n's have to eventually be non-increasing. This can be a little bit difficult to prove, so I'll show you an easy way to do it. The easy way to do it is to treat your sequence as a continuous function. And remember, we're allowed to do that back from section 1. So we're going to create a function f of x to just be 10x over x squared plus 16. Now, if you ever want to see if a function is decreasing, you just want to take the derivative and see when the derivative is negative. So here we're going to take the derivative. We have to do a quotient rule here. So the bottom times the derivative of the top minus the top times the derivative of the bottom divided by the bottom squared. Cleaning this up a little bit, we get this down here. Remember that this is the derivative, and as long as the derivative is negative, the original function is decreasing. I think the easiest way to check to see if a function is negative is just use the calculator or use a graph. So I graphed it over here in Desmos. So here's our derivative, 10, 16 minus x squared divided by x squared plus 16 all squared. So as I'm looking at positive index values, notice that it's actually above 0 between 0 and 4. So it starts off increasing, but after 4, I am below the x-axis, so I'm decreasing as long as my index values are beyond 4. So to check when the derivative is negative, from the graph, we see that the derivative is negative as long as n is greater than 4. Thus, my use of n is non-increasing for n greater than 4, and thus my 2 is satisfied. My use of n sequence values are non-increasing. The last part here, 3, remember is that we have to make sure our use of n's are going to 0. So if I plug n to be infinity, the denominator will increase faster than the numerator, or you could do L'Hopital's rule. Pretty easy to see that this does actually go to 0. All 3 of the conditions are satisfied. Thus, by the alternating series test, we have our series converges. One last little definition here. A convergent series that is not absolutely convergent is conditionally convergent. Conditionally convergent is the definition that we're looking at here. Remember that we looked at absolute convergence in section 5. Absolute convergence means not only does the sequence converge, but the absolute value converges as well. Conditionally convergent means that the series converges, but the absolute value does not converge. A good example of that would be the harmonic series we just looked at. The alternating harmonic series does converge, but if we were to take the absolute value and turn this into the harmonic series, it no longer converges. So the alternating harmonic series is an example of conditional convergence.